Let's discuss that a little bit more because that's fascinating. It's this compressed deployable structure that's based on like an origami design, right? And then you shipped it all the way to the North Pole, Greenland, and expanded it on site and lived in there for 60 days. Is that right?
Yes, that's completely correct. And listening to you explain it, it also sounds like I can hear how it sounds. It sounds like a crazy project, and it was. But what we set out to do was to test. So there has been done simulation missions all around the world. In space language, you call it like analog missions, and it's basically where you put some people together in in an environment that is realistic to outer space, to the stressors that astronauts would experience in outer space. There's one on the top of a volcano, there's one in the desert. We've also built something for an analog mission in the desert simulating Mars.
In Israel, right?
In Israel, exactly, yeah, in the Negev desert of Israel. But so there are these all around the world. The problem is, like, first of all, the architecture in many of these places are secondary. Like it takes a lot of funding to do research like this, and so the architecture is not a priority. So it's secondary. So they often take like old silos or like corn storage units and retrofit it because then it has about the dimensions of a rocket, stuff like that. And what we wanted to do was say, okay, what if architecture's first? Like our entire mission was to test architecture, because we believe that architecture, you can design it as a countermeasure for some of the stress that astronauts experience. But then to test the architecture, it was also important that we simulated a realistic environment. And in realistic, I mean like a real stressful environment, because we cannot test how the architecture works as countermeasure if it's not a stressful environment, right? Like
that's what's so great about your company. Like going through architecture school, professors encourage us to come up with all these outrageous designs. It's just designed for the sake of design. But you all have gone a step further, and you all have designed intentionally. Like every decision you make has an intention, and then you go another step and go and test it out in extreme conditions. I mean, we can't mimic the exact conditions on the moon and Mars, but you're coming as close to it as you can.
Yes, yeah, you're absolutely right. It's like we basically sat down and had a long talk about where on Earth is the most realistic place if you want to test something that's going to the moon. And basically you have the poles, you have the South Pole and the North Pole. Because we were in Denmark, because of logistics, getting to the North Pole is much easier than getting to the South Pole. There's also that, just like logistics in the South Pole is just a factor more difficult than the North Pole. But yeah, so the North Pole is great because it's isolated. You are completely far away from everything. If you fall and break your leg, you have to treat it yourself. Yeah, and that creates stress because you're always, every time you pick up a power tool, like every time we had to fix something, you're very afraid of cutting yourself, because the road to the hospital is like 3 days. Like it's if the helicopter can even come and get you, right? So it's like, so it's isolated. Then the lighting conditions are similar to the moon. We had 30 days of sunlight in the beginning where the sun didn't go below the horizon. The last 30 days of the expedition, the sun didn't rise above the horizon, right? So it was completely dark. And that also creates stress. That you have the cold, so it's extremely cold. So that also forces you to be inside the 4.5 square meter habitat all the time, basically, because being outside is minus 30 degrees Celsius, and the wind chill is like minus 41. And I know it's minus 41 because minus 41 is where Celsius and Fahrenheit kind of overlap. So that's for the Americans out there, I guess. So we chose that site very carefully. And then we spent 9 months developing the origami pattern that can fold. In the beginning of the project, we reached out to all the people in the world that we could find. Robert Lang from NASA, like a mathematician, an origami expert. And he said, guys, super interesting project. I thought about it before. It's not possible but I'll work on it for $300 an hour or something like that. And we were like, at that point, it was just me and Carl sitting, like together, and we were like, we almost couldn't afford food, right? Because everything, all the money we got, we would spend on like developing this thing. So we were like, okay, fuck it, we'll do it ourselves. And then we spent 9 months developing the origami until we finally had a geometry that would fold. And the funny thing is, he was right. Theoretically, it's not possible, but because he didn't take into account the flexibility and the stretch that is in the materials in the real world, it was actually possible. So it was just about finding and
the right material to use.
Exactly, the right material to use and the right dimensioning of that material.
So what material did you use? Was it like an aluminum frame with the material stretched over it?
No, so yeah, so the entire structural part of the habitat is aluminum, and there's two practical reasons for that. First of all, three reasons. So first of all, it's lightweight. That's great. We were two people moving this, even though it was a lightweight habitat. It's still like a 800 kilo structure you need to move around. Two people in the Arctic. It's still pretty heavy. But so it's lightweight. It performs great in the cold. You don't want to touch it because that'll give you frostbite real quick because it transfers like heat. It's very heat conductive. But and then the third reason, which I think is also one of the most important reasons, is we could machine it ourselves. Like aluminum is softer than steel. Of course, you need a little bit more thickness and stuff like that, but we can machine it ourselves. And since we were building everything ourselves, that was very important. So that's the structural part. Then the envelope, like the actual origami shell that folds, that keeps a pressure inside and keeps us safe and warm inside, that's made out of carbon fiber. So it's actually these sandwich panels, which is first like 0.5 millimeter of carbon fiber, then I believe it's 9 millimeters of like an insulation foam, a hard rigid armor cell insulation foam, and then another 0.5 millimeter of carbon fiber. So it's practically like these 9 millimeters sheets of sandwich panels that are super lightweight and super strong, like very stiff and very strong.
But really good insulators.
They are okay insulators. Like for its thickness, it's a good insulator. But we still had to add on like another level of insulation on top of that on the inside. But
did you all look into aerogel blankets?
We did. We looked a lot at aerogel, and you just go up in like. I mean, that would be nice. Like we would love to do that, but you just go up in price. Like carbon fiber already is it's so difficult. Exactly, and also getting that volume. I think we had 43 square meters of insulation in the habitat, if I remember correctly. Is that no? That can't be right. I don't know. It's such a long time.
Pretty expensive.
Yeah, but it would have been expensive, right?
Yeah.
But in the habitat, the flexible seam was a rubber with a nylon fiber in it, and that was like the key. That was like the golden key that made this whole thing work. So it took a long time to find a material that was flexible enough to fold and do the folding, but that could stretch enough to give us the tolerances for the entire structure, and that was strong enough that it could actually, because in Greenland you have some of this, where we are from the ice caps, you have like these very strong winds, these fall winds that are some of the strongest winds ever recorded in human history.
So it can't be too rigid because it'll topple over. It needs some sort of movement. Is that it?
It needs a little bit of movement, but it also needs to be rigid enough that it doesn't just like, so it's not like a tent that's just like standing, and yeah. So it was all a balance, and like this combination of these two materials, like the carbon fiber and the rubber, was like it.
And you all went there in 2020, correct?
Yeah, so we went there.
The rest of the world was isolating in their homes. You all isolated in Greenland.
Yeah, and the crazy thing was, so first of all, developing something like this and doing all the logistics while Corona is happening was the worst thing I've ever tried. Like, we were the only research project the only research expedition in Greenland in that entire season.
Oh my gosh.
All the research projects were just falling like flies. And we were like, but the only reason why I think we succeeded was because we were independent. All the other research projects, they were run
Funded
mainly, yeah, but by like universities and these large
by
organizational structures that were hit very hard by COVID. But because we were independent, we could take higher risk. We were sending ourselves, like I can take personally as much risk as I want. So we were a bit more agile and we could navigate the restrictions much easier. So yeah, so we made it work. But when we were there, we didn't have internet. So we actually thought that when we got back, that COVID would be like
over.
gone. We were very surprised when we land. Like after, you know, our entire expedition was 3 months. We lived 2 months inside the habitat, but it took us 1 month to set the camp up and unfold everything. So we were gone for almost 100 days. And when we got back, we were very surprised that, you know, we still had to wear like face masks and all of that.